Hello everyone, my name is Mateusz Pusz. Today we are going to talk about the software engineering and actually about the architecture part of it. And we'll talk about things that has to be considered during designing of interfaces, architecture, some projects and products. You will find out that there is no good answer in many cases. Sometimes there is answer A and answer B. Both of them have some benefits, but both of them have some problems. And then you have to choose which one to select. There's no golden bullet. You have to make some compromise. And basically, the engineering here is about trade-offs. This is the talk and the title for today's talk. Let's start with some introduction. Now it works. So let's talk about the art of the software design. When me as an architect, solution or software architect, when I'm talking to customers about the product they want to get, it turns out that it's really hard to find what they actually want, because it depends whom you are talking to. When I'm talking with developers, they want one thing. When I speaking with architects, they want something different. When I'm talking with managers, they want something different again. Everyone has its own point of view, its own requirements and constraints they want to achieve here or place on the product. And sometimes even the requirements are conflicting with each other, and you have to resolve them, right? So first, we have to get the requirements from all of the stakeholders and try to find a wide view, high-level view on everything that has to be incorporated into the product. So being able to see the whole picture is really important, because sometimes those stakeholders that talk to you basically see their own playground, right? The small piece of the entire puzzle. And sometimes they don't see that there is something that is really crucial and not stable and somewhere below, because they don't care about it, and you have to be able to find it, determine it, and maybe find a solution for it, a replacement, or make it stronger. And as I said already during introduction, sometimes there's more than one way to do it. If there is the best one, and then great, just choose it. Unless it's maybe too expensive to develop, to implement, then you have to make some trade-offs again. But let's not talk about the resources. Let's not talk about timelines today. Let's talk about technical problems only. And still, you may find out different solutions from the technical point of view that have some benefits, but also some problems. And you have to make some trade-offs. And sometimes you are thinking about which solution to choose even longer than actually you need time to implement this. So through the rest of this talk, we are going to put ourselves in the product architect's shoes. We are going to discuss some products, some potential problems, some potential solutions to those, and we'll try to find out through the polls that I will ask you to submit, which solution would you prefer as an architect. Let's start with exception safety and variant. For the very beginning, let's assume that you have some library that basically is about some networking. So we want to establish connections. We have the list of connections, some maybe ports or addresses from first to last. And we want to establish these 20 connections at the beginning of the application. If something fails, we have exception handling here. Our connection is really simple. It takes the port to connect. But sometimes, if something bad happens, we may have an exception. I don't know, network is down, or database is down, or whatever, right? And we have some getter to get the port, and the port stored here. We have vector of those connections. And our established connections may look like this one, right? We have retry number, retry count equals 10. And while connections are not empty, and basically our port is different than the last expected one, we are trying to establish a connection. So we are going to the next connection to establish and call add connection. If something is failing, we catch the exception. We are decrementing the retry counter, logging the issue in our log, and retrying. When the retry count is exceeded, we are just logging that we failed to establish connections, and we are rethrowing the exception to the upper scope. And this library can be really simple, assuming that you are using strong exception safety guarantees. Our add connection can just be connections and placeback of our port. And you don't have to care about any error handling here. And now I have a question to you. Probably you are aware of exception safety guarantees, right? Most of the people I talk to, they are aware of it. But how often do you analyze exception safety of your code that you just written? What was the last time you reviewed the exception safety of your algorithm written by you? How often do you analyze exception safety of your custom class assignment operator, for example? Yesterday during workshop, I had like 25 people in the class, and I asked them, and first we were talking about exception safety guarantees. Later on we had an exercise, and when we finished, I asked people how many of them actually analyzed the exception safety of their assignment operator. And only one person raised the hand from 25 people, even though we were talking about exception safety guarantees like 10 minutes earlier. This is something that we are not doing too often. Which exception safety guarantees basically your library, utility written by you provides, right? Ask those questions to yourself and try to find out what is the reason that actually we don't actually put it into practice, even though we know what exception safety guarantees are. If we don't know, here they are. There are 4 exception safety guarantees in the language. We have no-throw or no-fail exception safety guarantee, strong, basic, and no exception guarantee. Only in case of no exception guarantee, everything can happen. Application may crash, you may have blue screen of death or kernel panic or whatever in your application, because basically the program state is undefined. And this is a big problem. You should not code like this one. But all other are quite fine. No throw, of course, means that there will be exception will never happen. Exception will never, for example, leave this function. And then we have strong and basic. Strong exception safety guarantee means that even if their exception will happen in execution of some function, for example, then the state of the application, when you catch the exception outside of this function, is like this function was never called, like it never happened. So the basically state of the application, state of your classes, of your objects, are as they were before calling this function. So it means that if this function already did something up to the point of the exception, it has to undo all of the operations in order to restore the state to the previous one before it was called. With basic exception safety guarantee, this undo operation is not provided, it's not mandated. And the application has to remain in a valid state, then let's say documented state, so the user knows how to handle this one, but it doesn't have to be clear state like in the previous case. So the user may need to do some cleanup after exception handling. Of course, strong exception safety guarantee is better, but often it comes with a cost, for example, performance cost. So sometimes we agree on basic only to, for example, increase the performance. So my observation, as I already said, even if theoretically known to developers, exception safety guarantees are often ignored in the production code. Imagine that we didn't care about exception safety guarantees while we were designing standard library. And we ended up with a standard library that supports basic exception safety guarantee instead of the strong one. How this add connection function will look like in such a case? For example, it could be implemented like this one, right? If there are any connections, take the last iterator, and verify if this iterator maybe is dirty, so something bad happened, the element is in an invalid state, some cleanup is needed. So you have to erase this element that failed to be added, and then try to emplace back again, right? This would be really hard for everyone in the world to program like this with such simple stuff like std_vector or std_string or whatever, right? Strong exception safety guarantee allows us to write the code much easier than this one. If we didn't think about this before, we could end up with such a solution. And this would be a drawback for many developers around the world. Why I'm talking about this? Because most of the standard library provides strong exception safety guarantees, but there are some notable exceptions from this rule. One of them is variant, std variant. Variant has this strange values by exception state. By definition, variant cannot be empty. Empty is an invalid state of variant. Basically, it shouldn't happen. Basically, variant always stores one of the alternatives. However, if you have two alternatives and you are on alternative A and you want to switch to alternative B, and in order to do this, first you have to destroy A, right? And then during initialization, creation of the alternative B, the exception will be thrown. You cannot provide exception guarantee easily, right? Because you already destroyed A, so you cannot undo this operation. And B is not done. So basically, you are ending with some invalid empty state that basically is out of normal state diagram of variant, right? So this is some exceptional state, not a typical case of this utility. And this was one of the major engineering trade-offs we had to do for C++17 in the ISO committee. I was not there actually when it was standardized. I joined the committee when C++17 was done, but probably it was one of the really important decisions and discussions how to implement variant, because this is different than established practice, because boost variant did it in a different way. Let's see what are the side effects of having such a design. For example, we have basic socket and a fast socket. Fast socket sometimes during, for example, copy construction can throw because something bad happened. I don't know, drivers are not installed for let's say kernel bypass driver or whatever. And we have a variant. Our socket will be a variant of basic socket and fast socket. We have function process that takes the socket, establishes connections like in the previous slides we had, and then tries to set socket to a fast one. Assigns fast socket to the socket. Because by default, variant starts with a basic socket, because variant always by default is constructed with the first alternative. And we always get basic for free here, because it's always there. And if it's possible, we can end up with a fast socket. But if it's not, then we end up with this exception. And now, if you want to call our function process, it may look like this one. We have socket, we have function process that takes the socket, and then we are catching the exception. When we are catching the exception, we may want to check if actually variant, our socket, is invalid by exception state. It means that basically it failed to establish fast socket. So we have to revert it back to the basic one manually. It doesn't happen for free. It is not being done for us by the library. This is the side effect of having the basic exception safety guarantee in a variant. So it behaves differently than most of the other tools in the library. There are, of course, alternative designs. For example, a boost variant has a different assumptions. It's never empty guarantee. In case of potentially throwing copy construction, this is what is being done. We are copying constructing the content of the left-hand side to the heap as a backup, right? So we are dynamically allocating memory and backupping current state on the heap. Then you are destroying left-hand side, copy constructing the content of right-hand side. If there is an exception, so we couldn't establish our fast socket in this case, we copy our basic socket back to the left-hand side, right? So we just undid our operation. If everything is fine and we are able to establish this fast socket, then the basic socket is being destructed on the heap. And the memory is being freed, of course. So Boost variant provides a strong exception safety guarantee with potential cost of a dynamic memory allocation. Additionally, Boost variant does not provide any allocator support. And now we have to choose. Which solution do you think is better? Is it better to stick to strong exception safety guarantees, so it's easier to code? Or maybe we should basically limit number of allocations or basically disallow allocations for variant, like standard library did. So dynamic allocations are not allowed there for the variant. So we have solution 1, variant, basic exception safety only, invalid state is possible, you have to manually clean up if exception happens, but it never allocates memory. It can easily be used in restricted environments, like embedded, for example. Or do you prefer solution 2? I'm just running the poll for you right now, and let's see what will be the results. And solution 2 provides exception safety guarantees, strong ones, so there is no invalid state, no need for manual cleanup, but it allocates. So it may be slow, it may fail, right? Because heap allocation always may fail. There's no allocator support, so you don't have any control over it, how the memory is being allocated. And some projects will just not be allowed to use this utility, right? Like embedded, safety critical, hard real time, because they cannot afford having dynamic allocations in their code. And let's see how the poll is going. So far, 57% people voted, nearly 60%. And I see 70% for variant, 30%, sorry, for stud variant, 70%, and 30% for boost variant. So this actually is quite encouraging. It seems that the standard committee made a good choice here, that we preferred to disallow allocations with the cost of exception safety guarantees. Yes, and okay, we are going to end the poll in like 5 seconds. So the final results are 72% for stud variant, 28% for boost variant. This is the official result for this decision. So as you can see, sometimes there is no good choice, right? There are always some trade-offs. We are not going to talk about this right now because we don't have much time on this lecture. But another point we could be implementing for implementation, for example, to string. And this time, the trade-off is not on the ISOC+ committee side, because the API is the same, but the implementation details may differ. If you will, for example, compare string implemented by libc++ and libc2c++, and for example, Foley library, you'll find out that they differ. They provide different trade-offs. one of them is bigger, like 32 bytes, for example, with only 16 bytes of static storage. But it's really fast in runtime because there are nearly no branches to find out in which mode you are, small string optimization or the dynamic allocation. There are alternatives that, for example, are 24 bytes, so smaller. And all 24 bytes can be reused for storing internal data for small string optimization. But then every member function has to check if you are in the small string optimization mode or the dynamic allocation mode. So there is a runtime cost for those branches. There is a question, what does it mean by no allocator support in case of boost variant? By this I mean that boost variant doesn't take an allocator type in the template parameter, like for example all of the containers do. So you cannot provide a custom allocator that will allocate the memory according to your needs and expectations. Okay, as I said, instead of talking about the stud string, you probably know about those designs. I would like to actually ask you to help me design the Units library that I'm working on, that possibly, maybe in the future will be part of C++26. The library is called MPUnits, and this is a physical Units library. And there are two issues right now that I'm working on, and that basically, again, do not have one clear solution that will be the best one. First, let's discuss what's a quantity. A quantity is a property of a phenomenon, body, or substance, where the property has a magnitude that can be expressed by means of a number and a reference. A reference can be a measurement unit. This is official definition from ISO 80000. And examples of quantities are, for example, 123 kilometers of length, 70 kilometers per hour of speed. Those are quantities, right? So the class template that I ended up with looks as follows. It has dimension that describes basically the physical dimension we are working with, like length or speed, unit, so meter, kilometer per hour, and the representation type, how we want to represent the value. By default, it points to double. This is quite verbose. If you want to basically define a new variable on the stack, you have to print a lot of characters, right? Type a lot of characters. You have to provide quantity of dimension length, and then provide unit kilometer, and then you can provide the value. If you don't want to use default double, you have to provide even more parameters. It works, but it's inconvenient. In order to improve the user experience, we want to provide some helpers. And there are some alternatives here. Solution number one, I call them dimension-specific aliases. Those aliases are provided for quantities of each dimension. So for example, I have an alias template that sets dim length for this alias length and dim speed for alias speed. And unit and the presentation type are still provided to be set by the user. So if you want to create the length of kilometers in kilometers, you spell this like this one. If you want to have a speed in kilometer per hour in the integer presentation type, you provide it this way. This is quite fine. It's for sure it's cheap to standardize because there's only one alias per dimension, and dimension number is finite, so it's not that much. It's fast to compile because alias templates are one of the fastest to compile, according to rule of Chill that I was discussing at my other talks. Works both for literals and regular variables. So you can provide here a compile time known value or a function argument, and it will be working fine for both cases. However, it has some issues. It's still quite verbose to type. for example, namespace, like this SI, has to repeat it twice. And probably there will be even more. It will be like probably std colon units colon SI and then speed, right? So it would have to be repeated even longer part of the namespace name here. Also, class template argument deduction for alias templates do not work in this case. So you cannot deduce the representation type from the initializer. So I cannot just assume that this will be deduced from this initializer, because the unit will not be able to be determined from the initializer as well. So let's look for some other solutions. We may have unit-specific aliases. So not only for dimension, but for each unit. Each and every unit in the library will get its own alias. We have right now namespace called length, namespace called speed. So right now the dimensions started to be namespaces. And in those namespaces, we store those aliases to each and every unit, like kilometer and kilometer per hour. First of all, this is shorter to type than entire kilometer per hour, like here. Second point here is that only representation type was left for the user. And this means that actually new C+20 feature, so class template argument deduction for alias templates, will start to work here. So you'll be able to deduce the representation type based on the initializer. So let's see. This is how it looks in the code. SI length kilometer. You don't have to retype the namespace again because you provide it only once. You can either use the default or provide integer, or you can use ctat, right? As I said already. Or even, as this was an inline namespace, you can actually here provide using the declaration that's a bit longer, and then just use shorthand version of those units. So just kilometer per hour with the value, and everything will work as expected. So depending on your needs, you can either be verbose or terse. It's up to you to decide how you want to treat your code in specific scope. Because you may decide to have different approach in one scope and a different approach in other scope, right? Because it depends how easy to read and maintain this code will be. So, good sides of this solution. It's still fast to compile because those are alias templates. It works both for literals and regular variables again. And user can choose to either use a long or terse version. Problems that we can find here? Basically, it will be quite expensive to standardize because we have to standardize the alias for each and every unit in the library. And there are quite a lot of units for each dimension. Like, for example, for length or for time, you will have all of the kinds of seconds, right? Like nanoseconds, picoseconds, and so on. And the same for meters and so on. So a lot of units. Okay, so let's move to solution 3. Solution 3 is provided for named units only. So only for those that has their own name, like kilometer, like hour, but we don't have to, for example, provide a unit for kilometer per hour because it will be able to be constructed on the fly, as I will show you on the next slide. This means that I'm creating a new type that actually it's still in the library. So actually it's nothing new. It's just reusing the type that is there. It's called reference. So if you remember from the definition of quantity, quantity was a number and a reference, right? So this matches nicely the definition. Reference provides the information about the dimension and the unit. And we have kilometers, we have hours. And then, if you want to use it, you're using this in this way. So we are multiplying the value by the reference, and we are getting a quantity from this. As I said, as you can see here, we don't need a kilometer per hour that's being provided by the library, because you can just divide kilometer by hour and you will end up with kilometer per hour anyway. Additionally, you can easily create your own reference if you need. If you prefer to type kilometer per hour, you can just spell this one and name it auto, and then just use it for your convenience. So it's really easy to extend if needed, but from the standardization point of view, it's less to standardize than in the previous case. So again, good sides. Medium effort to standardize, because it's provided only for named units, works both for literal and regular variables, easy to compose custom references for unnamed direct units. Problems. Slower to compile, because this is not an alias template, this is a class template instantiation, which is slower during compile times. Sometimes it may be awkward to type. For example, this is 20 meters per second divided by 10 meters per second squared. So the speed divided by acceleration. Objects with short names often shadow users' local variables. I'm pretty sure that in your code base I can find already variables and object with the name M, T, or big N, right? So this is meter, ton, for example, and Newton. And those may collide. And sometimes it may be hard to understand because the syntax is even two terms sometimes. It's fine if you have a number like 1, 2, 3 instead in front of this multiplication operator here, but if you're using arguments with a short name, then D multiplied by M divided by T multiplied by S may not be the easiest one to read, right? And we have solution 4. Solution 4, like we know from the basically std.chrono library. We have user-defined literals. And for each unit in the library, we provide two versions, one for the integral version and one for the floating point version. So it is twice more than in previous cases for each unit in the library. Also, you don't have any control over the representation type. It can be either huge integral or huge floating point. You cannot use int, you cannot use short. It will always end up with the biggest possible type. Also, literals work only with numbers, right? With compile time known values. In this case, you cannot specify, for example, function argument in front of the user-defined literal. So basically, the scope of usage is limited, and from my basically experience, is limited to, let's say, physical constants or unit tests, because in unit tests you often work with hard-coded values, right? But in the official business logic code, in most cases it is not useful, because then you have variables with some values rather than compile time known literals values here, numbers. But it is something that we are used to, right? We are already working with this in Chrono. And I had to provide this Q disambiguator here in front of the literal because some of the units collided with what we already have in compilers. So it cannot be just kilometer like in case of Chrono. Pros. This is what we know already and what we use. Terse and easy to understand. But there is a huge list of disadvantages, right? Is the slowest to compile, the most expensive to standardize, works only for literals, you have no control over representation type, and if you have the same user-defined literal in different namespaces, like for example SI and CGS systems, then there is no way to disambiguate those, because you cannot put namespace name in front of UDL. There's just no way to do it. Of course, you may say, well, if you provide all of this in the library and you already implemented this one, then just provide everything for the standard, right? But no, this is not a good solution, right? Standardization takes time. time is needed to discuss stuff in the working groups, to prepare ISO specification, to implement by all of the vendors in the standard library, and then for the trainers and for the and for engineers to teach and learn, right? If there will be 4 ways to do so, probably it will not be the best solution. So just to quickly compare how it looks and feels for each solution, and I'm starting the second poll for you. So solution number 1, dimension aliases. Looks like this one. Quite verbose, but small effort. Unit aliases. Shorter, and being able to provide different verbosity if needed. Quantity references. Really nice to work with. We know it from Boost already and other libraries, but also had some issues. And user-defined literals. Something we know from standard library. I also have a comparison in such a table with all of the solutions and all of the factors here. When you see blue, it means that it's the best solution in specific column. So you have all of the alternatives here and the support for literals and variables, preserves user-provided representation types, explicit control over representation type, readability, possibility to resolve ambiguity between different namespaces, hard to resolve shadowing issues in case of small objects, I mean like short names or identifiers of the objects, right? Like M, N, and so on. Controlled verbosity, easy composition for derived units, implementation and standardization effort, and compile time performance. And let's see which one would you like to see in the future standard version. The poll is running. About half of the people voted already. Actually, the answers here are quite interesting because I ran the same poll a week ago in the Menic user group meetup that we met. And at this time, if I remember correctly, the community preferred option 3 and 1. And now I see that clear winner is option 2, unit aliases. Unit aliases right now has 56% of all of the votes. Dimension aliases have 16, references have 19, and UDLs have 8. So it seems that in this case, the community would prefer unit aliases as the best solution for going on. Okay, if you would like to get more experience with this feature, please go and try our library, provide feedback, how it works for you, what if actual unit aliases are the best one, or maybe you'd prefer references, because maybe you just need more hands-on experience, right? But we are looking for feedback on those one, right? Because we want to standardize it in next years. And we have to find out which solution works the best for you, not for us, right? So please try it and provide the feedback. Actually, the library actually compiles fine with every major compiler on the market right now. The latest version, of course, but still, every compiler is supported. By every, I mean, of course, Visual Studio, Clang, and GCC. And sorry for other vendors if I missed them. Okay, so let's close this poll and let's move to the last case for today. The Donecasting facility. Maybe you've heard one of my talks previously on the library and the Donecasting facility when I was providing information how nice it is and how it's implemented. I will not provide the information how it's implemented today because we don't have much time, but I will show you what it does and what are the benefits of it. For example, if you have average speed function that takes some length and some time here, this is function template that's constrained by two concepts, length and time. Also returns speed, right? And this function basically divides the length and time to get the speed, prints the speed on the screen, and returns speed to the user. and we are storing speed here. When we print this, well, actually run this application, this printing will print 70 kilometers per hour. It knows that this is speed in the unit of kilometer per hour. If you'll go to the debugger, you will actually find out that this is true. The type of our S here will be the quantity of dimension speed in kilometer per hour unit with integer representation. So the Donecasting facility allows us to take length and time, do some template metaprogramming magic to find what is the dimensional equation for the result, and then find out that this dimensional equation result is actually the predefined type provided by the user called speed. This is how it looks in the hierarchy, but I will not scope much more on the implementation here. So this is what is constructed by the engine. This is this result of the equation. And then, thanks to the Donecasting facility, we can find this type that user provided as a child class of this one. So Donecasting facility can be considered like a typecasting engine. That basically every time it sees something like this, it converts the type to something like this. However, there are some issues connected to this. It's great, it has a lot of benefits, but issues are actually really important here. There is something called one definition rule. One definition rule is provided for two different scopes, for translation unit and a program. In case of translation unit, the rules are really simple. There can be only one definition of anything in one translation unit, right? This is why we provide all of those header guards in our header files, so the definition is not repeated in the same translation unit, because it will be a compile time error, and basically will make one definition rule violation. And there's another scope for entire program, and that one and only one definition of every non-inline function or variable can appear in an entire program. If it's an inline function or variable, it has to be provided in every translation unit that wants to use it, right? Because otherwise you will not be able to inline it. And in case of class, it's also required to appear in every translation unit that wants to use it. It seems simple, but as this is C++, of course we have some exceptions, right? So there is but. There can be more than one definition in a program, as long as each definition appears in a different translation unit, because in the same translation unit we already decided that it's invalid to have repeated definitions. And each definition consists of the same sequence of tokens on the lexer basis. So it has to be exactly the same. And now let's see how it relates to our problem. We have our average speed in a header file. We have translation unit 1 that includes average speed header. It includes the speed definition, so we know exactly that this is speed class that is the result of this dimensional equation here. While we are calling this function, we are ending up with this stuff on this text on the console, also with this nicely typed type that we've seen before. However, in the second translation unit, you will forget about providing this header file. You will end up with something like this one, a raw result of dimensional equation. Because the engine will not be aware of the customization point provided by the user, of this special type that user created for this result of dimensional equation, right? So if there is no definition in the translation unit, the engine cannot provide it. I just want to point here that it's not something bad or different than what we have already. This is how some customization points behave. Right? Let's, for example, consider some A-B header that defines A and B. A has some value, B has a value, and a pointer to A. And it provides streaming operator. How to print it? And in one translation unit, we provide swap. And we are specifying that we want to swap only values of B. And we are not swapping pointers of A. I don't know what's the reason for this, but someone decided that's a wise way to do it. Right? So we are defining here A1, A2, B1, B2, that refers to A1 and A2. And we are doing stud ranges swap. The result of the streaming operator will be 2, 1, 1, 2, right? Because we swapped only values of B and values of A remained as it was initialized. If you provide another translation unit that will not have the swap definition, we are ending up with stud swap definition. That basically will swap entire data, and we are ending up with a different result. So this is exactly the same problem. There is a default implementation for stud swap that does the trick and basically compiles fine. And only if the user provided customization point is visible, is defined in the translation unit, is being used. Otherwise, the default is chosen. This is in case of swap. So swap is special in this case, but most of the customization points we have. So I don't want to say that customization points are bad in any way, right? Because most of the customization points we have will not compile at all if they are not provided. For example, let's consider that we forgot to provide this streaming operator. This is another customization point, right? We want to provide this on the console, and we'll end up with compile time error saying we don't know how to print this to console because there is no customization point provided. This is a typical use case for most of the customization points. Swap is different because swap has a default implementation for every type. We don't know how to print every type, so we didn't provide any default implementation. Maybe we'll provide one when we have reflection in the language, right? But for now, there is no possibility to do so. So we have three alternatives here. What to do with this Donecasting facility? Well, we can say it is great, and so keep it as it is. We get the speed when such definition is included by the user. So we have nice console errors and console outputs. We have nice types in the debugger. We have nice types in the compiler errors. Or because otherwise we would end up with unknown dimension, exponent length, exponent time, not speed. In order for the users to be aware of such a possible issue, we have to document the fact that the physical system definition has to be the same in entire project. So you basically have to include the same set of header files with units definition in every translation unit of the project, because otherwise you risk one definition rule violation. And we hope that C++20 modules will help, because, for example, you can provide one module called SI, and it will automatically provide all of the definitions at once. But still, there may be some issues because, for example, we may have SI and CGS, and some translation units, people, for example, will forget about including CGS. Let's see solution number 2. Let's do a compile time error when the resulting dimension of units is undefined. Right? There is no support for an unknown dimension, so it will never compile. Everything will have to be predefined. Even if it's just partial result of some other arithmetic calculation, it won't compile for you. So, for example, things like this one will not be allowed. We have velocity in kilometers per hour. We have sync rate in meters per second, right? And then we are doing some temporary calculation, like squaring the velocity and sync rate, and this won't compile, because the result of the arithmetic calculation here will not be defined by the user because it's something strange, power of 2 of velocity, of speed, and this will not be found by any definition. And basically such code will not be possible. I actually see that people started to vote on the number 2 because I ran the poll a bit too early. So maybe I will end the poll and start it again because people probably were not aware of this issue. And sorry for that. I will try to rerun this poll again. If you still prefer 2, just continue with 2. But I just want to make sure that everyone is aware of this problem, right? And then if you want to square root the solution, then basically you're ending up again with a speed that's well defined. So everything is fine, but this will not be possible. And even this will not be possible, even though it's in the same line. Because still, the right-hand side here, the argument of square root here will end up as this squared dimension that's not defined by the user. So basically, such calculations will not be possible. And this may constrain the library a bit too much, in my opinion. But still, it's one of the valid solutions. Or the user should be responsible for providing a specific type, right? This is the first solution. So this one, S1 here ends up as, let's say, garbage, unknown dimension, exponent length, exponent time, strange stuff being printed on the console. But then you can assign from S1 to S2 that's already known and provided by the user. And if you print S2, it will print fine. If you will use S2 in the debugger or see a compiler error, it will be the type provided by the user. There will be no magic behind the engine, right? And getting rid of the Donecasting facility simplifies the standardization effort as well. But in such a case, this function will not be possible. The one that we analyzed. It will never print the correct solution because we will not know what should be the type of S. And just remember, it's not only about the printout, about the console, right? The most benefit of Donecasting facility is not output on the console. The biggest benefit is of having nice, clear error messages and nice debugging experience. Okay, so now we have all of the information, and it's time to poll. Choose the best solution. Which one would you prefer? Keep it as it is right now, so have all of these features with potential problem of one definition rule violation, and hope that modules will solve the solution. Have a compile time error, when some temporary evaluation is being done that was not predefined or predicted by the user. Or maybe get rid of entire facility and just ask user to provide explicitly the type. And until the type is not provided, we end up with some, let's say, a longer type, some garbage. But when the user provides a strong type, we end up with a nice solution. But then some functions, like ours, will be really hard to implement because we'll not be able to know what is the exact type in the middle of the function because user will not be able to provide it. Well, maybe as an additional template parameter, of course, or whatever, but the engine by itself will not deduce it. I'm looking into the poll. I see it's probably one of the hardest one because only half of the people voted so far. And we have really, really tough choice here. For now, we have 37% of people saying keep it as it is. 32% are for the 2 and 3. So there is a slightly preference for option 1, and 2 and 3 are the same, 32% right now. Let's wait maybe 15 more seconds to let other people to vote. What would they like to see here? But as you can see, this is not an easy choice. Okay, let's end the poll. The final result, keep it as it is, 40%, and 2 and 3 got 30%, so exactly the same. So as you can see, providing new facilities for everyone may be really hard. Designing is not easy. Different customers have various expectations, experience, constraints. Often, there is no golden bullet, no single solution that is clearly the best. And we have to choose from several suboptimal solutions, even if we know that this will make somebody not fully happy. C++ standardization takes time, right? So you cannot just standardize everything, all of the options. In order to make the best choices possible, we would really like to encourage early adopters to provide feedback and basically their requirements. Go and try my library. Go and try linear algebra library or any other library that is considered to be standardized in the nearest future. Provide feedback to the users, how it proves to you. What are the problems that you've seen? So we know, we have more information on choosing the best solution for the future. Because sometimes we don't know exactly what are your constraints, what are your requirements, what is your experience with the product. You have some possibility to influence how future standards will look like. So please go and try those libraries that are meant to be provided in the future versions of C++. And last but not least, naming is hard. Thank you very much. You can find more information about my library on this link on GitHub. I think there is quite good documentation of this one, so it should be really simple to start with. But in case you have any questions, please let me know. I will be really willing to help you in setting up the initial environment to start working with the project. And do we have any other questions that we didn't cover so far? I don't see any on the Q&A, but if you have one, we have some time to ask that. Like 2 minutes. Okay, I don't see any questions. If there will be any questions, if you would like to talk with me, I will be in the Gather Town, in the Track A room. So see you soon and have a great conference today.